Hello everyone. So this video talks about the slope deflection equations, its derivations, and the derivation of uh, fixed and forces for various loading or loading types. And if it is your first time in my YouTube channel, please don't forget to subscribe and click on the notification bell so that you will be updated of my videos to be uploaded in the future, which may be helpful in your preparation as a civil engineering student. And also, in that way, I will be inspired to do other videos which will be helpful in your studies. So I hope you don't forget that. And if you want to have comments on my videos in my lecture series, please do so, so that I will correct them if there are uh, errors, mistakes in my discussion. So, thank you. Today I'm going to discuss the slope deflection equations. So let's consider any continuous beam. And we have here the arbitrary loading. And let us draw the deflected shape, and let's assume that there is relative displacement between the near end and the far end. The length of the portion between N and F is denoted by L. Then we draw the tangents at N and F. So this is the relative displacement. Let's call that delta. Then the tangent at N rotates clockwise. Let's call that theta N. The tangent at F at the far end also rotates clockwise. So let's call that theta F. And the chord joining N and F rotates also clockwise. And the angle, remember, it's very small. Let's call that E. So everything is clockwise here. The rotation of the chord is also clockwise. So slope deflection equations assumes that clockwise rotation, clockwise moments positive. So remember, that's the assumption of the slope deflection equations. Clockwise rotation, clockwise moment positive. So let's draw the moment diagram by parts and its conjugate beam. So the moment, internal moment here, we do not include the moment due to the loading. This is purely due to the internal moment. So we have Mn over Ei here, Mf over Ei here. So this force equivalent to the area of the triangle is F1. And we have F2 here going down. And theta N, which is shear here, because positive shear is, because this is the left section, the positive shear is supposedly upward. But because the rotation is clockwise, that's negative, so it's downward, theta N. The distance between the centroids is, of course, because that's L over 3, this is also L over 3, so this is also L over 3. So that's theta N. The rotation here is also clockwise. The positive theta, because that's clockwise, the positive theta at the right section is also downward, but because that's clockwise, and the theta F should be upward. And the distance L over 3. So summation moment about point 2 equals 0. By the way, this is the moment, delta, because this delta is downward, negative. The positive moment is supposedly counterclockwise at the right section. Remember smiley bending? At the left side clockwise, at the right side counterclockwise. But because this is negative, the moment is clockwise, delta, at the right end. So summation moment about point 2 equals 0. So we have F1 times L over 3. By the way, the moments produced or contributed by the loads are called fixed end moments, and we will have a separate discussion of that, how to compute these fixed end moments. So summation moment about point 2 equals 0. So we have F1 times L over 3 plus delta equals theta n times 2/3 of L plus theta f times L over 3. So that's the equation. So we simplify by multiplying everything by, or multiplying everything by 3 divided by L. So this becomes 2 theta n after we multiply L over 3 over L, and this becomes theta f. Then this one, when we transpose to the right, we also multiply this by 3 over L, so minus 3 delta over L. Substitute the value of F1, which is the area of the upper triangle, 1/2 L times mn over EI times, yes. So we have 2 theta n plus theta f minus 3 delta over L. So multiplying everything by 2EI over L, and this expression here at the right. So Mn therefore equals 2EI over L times quantity 2 theta n plus theta f minus 3 times delta over L. So take note that the ratio delta over L is equal to P. You may replace this by P if you want. Similarly, if we derive M moment par, we just pattern the formula, which looks the same as this, except that we change subscript n here by f, and this n here would be f, and this f here will be n. So moment par equals 2ei over L, quantity theta n plus 2 theta f minus 3 delta over L. So it's the f that is times 2 this time. Next, adding the fixed end moments. So let's consider first this formula here, moment here. So 2ei over L, quantity 2 theta n plus theta f minus 3 times delta over L plus fixed end moment here. Similarly, moment par is 2ei over L, quantity theta n plus 2 theta f minus 3 delta over L plus fixed end moment par. So this is now the these are now the slope deflection equations. Note that delta over L is equal to P. So remember the sign conventions, and when you apply these slope deflection equations, clockwise, positive. And I will state later what is really the universally accepted sign convention for moments. So clockwise moments, clockwise rotation, then clockwise P, which is delta over L, are positive in these slope deflection equations. When the other end of the beam, say F, has its moment 0, so for example, the other end F is a ruler support or a pin support, we know that the moment at that end is 0. So that's the case. But it doesn't mean that the far end is the one that has ruler or pin support, or it doesn't mean that F or the far end is always
0. There is also a case where the near end is 0. So for instance, the near end is a ruler or feed support for that case. So in this situation, so let us say it's MF that is 0. Because if you're going to analyze these two formulas, you do not memorize these two. You just memorize familiar one, just the first. Because for the far end, you just replace n by the subscript f. So when the far end is 0, so this is the formula for near end, we do not include the effect of the loading. We just, or this is equation 1, sorry. Then equation 2, because moment f is 0, 2ei over L theta n plus 2 theta f minus 3 delta over L plus 6n moment. So the objective is to eliminate theta f. Since the formula for Mn is only theta f, so we multiply equation 1 by 2. So it becomes 2Mn equals 2ei over L. Then that 2 is distributed on the inside terms in this bracket. So we have 4 theta n plus 2 theta f minus 6 delta over L, then plus 2 times fixed end moment here. Now we subtract equation 2 from this equation here. So subtracting equation 2 from this equation here. So you will have 2mn minus 0. So it remains 2mn. Then 2ei over L, copy 2ei over L. Then we have theta n. We have 4 theta n minus theta n. So 3 theta n. 2 theta f will be eliminated. Negative 6 delta over L minus negative 3 delta over L will be negative 3 delta over L. Then plus 2 fixed end moment here minus fixed end moment far. So that will be the result. 2ei over L quantity 3 theta n minus 3 times delta over L plus 2 fixed end moment here minus fixed end moment far. Dividing everything by 2, then after we divide everything by 2, this 3 is common. We factor it outside. So Mn equals 3 ei over L times quantity theta near minus P or minus delta over L plus fixed end moment here minus 1/2 fixed end moment far. So you just familiar two equations. One is this and the other one is this. Remember that this Mn here and Mn here are not used for the near end only, but you can use these formulas for the far end. For the first formula, it means that you can use this formula here in two ways. So if we have a beam, left point and right point, if there are moments at the left or the near end and the far end, then that means you have to apply this formula twice. But when one of the ends of the beam has 0 moment, then use this second equation here because the other end has 0 moment. So that's the meaning of these two. So moment here is 2ei over L times 2 theta n plus theta f minus 3 times delta over L plus fixed end moment here. This is applied twice when both n and f have moments. So you can use this for the near end and you can use this for the far end because the two ends, n and f, have moments, have values for moments. But if one of them is 0, then use the other formula. Moment near equals 3ei over L times theta near minus delta over L plus fixed end moment near minus 1/2 fixed end moment far. So take note that this equation is used when one of the moments, either Mn or Mf, is 0. So let's consider these continuous beams. So at A, there is moment expected. At B, there is moment expected. At C, there is moment expected. At D, the moment is 0. So let us set up equations in order to show how these two equations here can be used when we set up the slope deflection equations for the different spans of the beam. So for span AB, the formula is applied twice or applicable twice. We have moment A to B. This is our near end. This is the far end. Then we have moment B to A. Then we have MBA. It means B is the near end and A is the far end. Similarly, if MBC means B is the near end, C is the far end, and we also have MCB because this equation is applied twice. So C is the near end and B is the far end for that case. Then for CD, because the far end D is a roller support, there's no moment here. It will just rotate. There's no resistance to rotation. So we only have one equation, and that's why we use equation 2 for span CD. So we have MCD only, and it is equal to 3EI over length of CD quantity theta C minus, by the way, delta over L is 0 because these are supports. There's no relative vertical movements of the supports for this case, unless otherwise there are settlements provided. But in this case, when there's no settlement, the supports remain intact, then delta over L will just be 0. So for span BC, the formula is applicable twice also. Then for span CD, it's only applicable once because moment at the far end is 0. So moment AB equals 2EI over L times quantity 2 times theta A, which is 0 because that's fixed end, plus theta B minus 3 times, as said, delta over L would be 0 for supports that do not settle, plus fixed end moment AB. Then moment BA is 2EI over LAB quantity 2 times theta B plus 0 theta A minus 3 times 0 plus fixed end moment BA. Then for BC, MBC equals 2EI over LBC quantity 2 theta B plus theta C minus 3 times 0 plus fixed end moment BC. Then MCB equals 2EI over LBC times quantity theta B plus 2 times theta C minus 3 times 0 plus fixed end moment CB. And finally, for CD, moment CD is 3EI over LCD times quantity theta C minus 0 plus fixed end moment CD minus 1/2 fixed end moment DC. So that's it if you set up equations by slope deflection equations. Now, let's now compute these fixed end moments. So let's discuss restrained beams and the fixed end moments. When the beam is fixed at both ends, which is if we have continuous beams here, remember that we imagine when we compute for the fixed end moments, we imagine that each span of the beam, regardless of the ends are fixed or not, are considered fixed when we compute fixed end moments. So imagine that span AB is fixed at both ends, BC is fixed at both ends, CD is fixed at both ends. So this is the near end, that's the far end. Let's consider first the case where we have a concentrated load or point load, and the distance of that load from N is A and from the far end is B, and the total length of the beam is L. So how to derive the fixed end moments or the moment at N and the moment at F? So first we have to apply area moment theorems here. Take note, the tangents at the near end and the far end are all horizontal. So theta NF, or the area of the moment diagram between N and F, or the change in rotation between N and F, is 0 because the tangent at N is horizontal, the tangent at F is horizontal. And the second equation is EI division of, say, N relative to the tangent at F, because the tangent at F is horizontal. It hits or it crosses n. So therefore, the deviation is the vertical deviation of n relative to the tangent of f is 0. So this is the deflected shape. And take note that the curvature of the support is really concave down. So supposedly we expect negative moments at the ends. So we only expect positive moments here because this curvature is concave up. So that's positive moment. But at the end, it's negative. But in our derivation, let's assume that moments are positive. So moment diagram by parts, we have first moment at f, which is assumed positive, and the moment at n, which are assumed positive. Remember, at the left end should be clockwise, and at the right end should be counterclockwise so that the beam will bend sway. So that's the assumption, but actually, moments expected at near end and far end would be negative. So first, due to the fixed moment at f, that's constant, we make n as the wall. Then the reaction at f, so this is mf, fixed moment f over ei, or mf over ei. Then we have vertical reaction at f, which is rf, then times l over ei. Then moment due to the load, which is the only negative here, is pa over ei. Because ei is constant, let's assume that ei is constant, or the fixed moments are not affected by the moment of inertia, because the moment of inertia will be set up only in this slope deflection equations here. So we have ei theta nf equals 0 and ei deviation of n relative to f equals 0. So these are the two equations in order to solve these two unknowns, reaction at f and fixed moment at f, in the formulation of the equation. So first, ei theta nf. By area moment theorem, this is simply the area between n and f. So 1/2 L times rf L plus fixed moment f times length, rectangle, then equals or minus or equals 1/2 of a times pa. So simplifying, we have rf L square over 2 plus fixed moment left equals 1/2 pa square over 2. Call that equation A. Then for division of n relative to f, so it's simply moment of areas with respect to n. So these are already the areas. So all you have to do is add or multiply these areas by the moment arms. For rf L square over 2, multiply L over 3. For fixed n moment f L, multiply L over 2. Then for pa square over 2, the moment arm or distance of centroid from the near end is a over 2. So again, rf L square over 2 times L over 3 plus fixed moment f L times L over 2 equals pa square over 2 times a over 3. So that's equation B. Now, we want to derive fixed moment left. So this is rfl square over 2, this is rfl cube over 6, so that we can eliminate rfl cube over 6, we multiply equation A by L over 3. So multiplying equation A by L over 3, it becomes rfl cube over 6 plus fixed moment f L square over 3 equals P square over 2 L over 3. So that's the result when we multiply L over 3 to equation A. Now that this equation is, this term here is similar to this term here, then we can now eliminate RFL cube over 6 by subtracting this equation here from equation B. After we subtract this equation here from equation B, we eliminated RFL cube over 6, then we have fixed moment L square over 2 minus fixed moment L square over 3, they are like terms. So 1/2 minus 1/3 is 1/6, so fixed end moment L square over 6. Then here, PA cube over 6 minus PA square L over 6. The common terms in the right side is PA square over 6. We factor that out. So what remains here is A. Then in the second term, it's minus L. Noting that A minus L is negative B because L is longer than A. So this is negative B. Then we cancel out 6. Divide everything by L square. We now have the fixed end moment formula for the far end. It is equal to PA negative PA square B over L square. So fixed end moment far L square over 6 is PA square times negative B. So finally, cancel out 6. Fixed end moment here is negative PA square B over L square. Therefore, the fixed end moment here is, we pattern the formula from here, is negative PA B square over L square. So that's the formula for fixed end moment here. Negative PA B square over L square. So the negative sign shows that the fixed end moments are really negative based on the curvature of the ends. So they are concave down, as I said. But when we derive the fixed end moment formulas, remember that we assume they are all positive, but the result gives us a correct sign of which is negative. So familiar just one formula for fixed end moment due to concentrated load. It is negative P, then times A, the distance of the concentrated load from the near end is A, in computing fixed end moment A. Then you square the distance of the fixed or concentrated load from the right end, then divide everything by L square. So that's the idea. And just memorize this, because if it is far, you just interchange the squared term. So this time, if you compute for fixed moment far, it's A that is squared, then B is now raised to 1 only, and over L squared. So that's due to concentrated load. We will call that equation formula equation 3. Then how about fixed moments due to uniform load over the entire span? So we anticipate that the fixed moments at the near end and the far ends are equal because of symmetry. So we will still use the area moment diagram first. Then in the second proof, we will use the result for concentrated load, and by integration to derive the fixed moment due to these uniform loads here. So again, we assume that the fixed moments are positive, though it should be clockwise. We look at the curvature so that it will bend that way. And here it should be counterclockwise. Here it should be clockwise. But let's just assume positive. The moment diagram by parts. So this time we have this moment due to the fixed moment near end. This time let's make the right wall. Let's make the right end as the wall. Then reaction at end times L over EI. Then EI does not affect our calculation for fixed moment. Just treat them one. Then moment due to the load, which is W times L over 2. So WL square over 2 negative over EI. So imagine that EI is 1. So for our first equation, EI theta and L equals 0. So add the upper areas, then equate to the lower area. So this is second degree. So EI theta and F equals 0. So 0 equals 1/2 of L Rn L plus fixed moment near times L minus 1/3 of L times WL square over 2. So therefore, Rn L square over 2 plus fixed moment near equals WL cube over 6. Equation 1. Equation C. Then EI deviation of F relative to N equals 0. This time, it's the moment of areas with respect to F. So we just multiply these terms, because these are areas, by the moment arms. So Rn L square over 2. The distance from the F is L over 3. Fixed moment near L times L over 2. Then W equals WL cube over 6 times L over 4, because this is second degree. So the distance is L over second degree plus 2. So L over 4. Then we multiply equation. We simplify this equation into Rn L cube over 6 plus fixed moment near L square over 2 equals WL 4 over 24. So that we can eliminate Rn L cube over 6, again we multiply equation C by L over 3. The result of the Rn L cube over 6 plus fixed moment near L square over 3 equals WL to the 4th over 18. Then, because we can now eliminate Rn L cube, we subtract equation C.1 from equation D. So Rn L cube over 6 is eliminated. Again, 1/2 minus 1/3 is 1/6. Fixed moment near L square, fixed moment near L square over 6. Then 1 over 24 minus 1 over 18 is negative WL to the 4th over 72. Multiply everything by 6 and divide by L square. So fixed moment near equals fixed moment far by symmetry equals negative WL square over 12. So fixed moments are really negative. Then let's use the formula fixed moment near equals due to concentrated load equals negative DAD square over L square this time. Then there's no concentrated load, so we consider a strip of length dx. Then the area of the strip is our differential P. So which is W, the height is W, the thickness is dx. So the differential P is W dx. Then the distance of this concentrated load from the near end is, we will call that x. So A is x, and the distance of this concentrated load from the right end will be B, and B is L minus x. So by the formula, fixed moment near equals, it should be in integral form because we consider differential here. Fixed moment near is equal to fixed moment power equals negative integral 0 to L. This is our P, or the force differential P W dx. Then A is x, B is L minus x. So B square, so L minus x quantity square, divided by L square. So fixed moment near equals fixed moment far equals negative W 0 to L over L square. Then we have L square, then times x, so L square x. The middle term is negative 2Lx times x, so negative 2Lx square. The last term is positive x square times x, so x cubed. So integrating, fixed moment near equals fixed moment far equals negative W over L square times L square x square over 2 minus 2Lx cubed over 3 plus x to the 4th over 4, 0 to L. Substituting, the lower limits would be, after we substitute the lower limits, everything would be 0. So they are like terms, 1/2 minus 2/3 plus 1/4 L to the 4th divided by L square. So that becomes negative WL square over 12. So fixed moment near equals fixed moment far equals negative WL square over 12. So we have the same result. Now, for this triangular loading, so we do the same thing. We consider a strip. You can also derive the formulas by same approach here by area moment. So we draw the moment diagram by parts if you want. But let's just use the result or fixed moment of a concentrated load because it's faster and we don't need to draw moment diagram. So we have here dp, which is equal to height of strip, which is y dx. And to solve for y by similar triangles, let's call this distance x. And this one is L minus x. B is L minus x. So A is x, B is L minus x. Then y as to x equals W as to L. So y is Wx over L. So fixed moment here therefore is equal to negative of integral 0 to L of y dx, where y is Wx over L. A is x, B is L minus x quantity square, then divided by L square. So simplifying, we have negative W over L cube, then integral of L square x square minus 2L x cube plus x to the fourth dx. So again, when we expand this, the first term is L square, then we have x square here. So it becomes L square x square. The middle term is negative 2lx times x square, so negative 2lx cube. The last term is x square times x square, so x to the fourth. So integrating, we have fixed moment here equals negative w over r cube times quantity L square x cube over 3 minus L x to the fourth over 2 plus x to the fifth over 5, 0 to L. So because the terms inside are like terms, so we have L to the fifth, right, inside, and we have L cube here. So the result is WL square something. So 1/3 minus 1/2 plus 1/5 is then times negative WL cube. The result would be fixed moment here is negative WL square over 30. Take note of that. That's the formula. You're going to memorize at the fixed end. At the right end, the fixed moment is greater because the intensity of load is higher at the F. So you do the same thing, then this time x is squared, L minus x would be power 1, and show that the result is negative WL square over 20. So fixed moment far is negative WL square over 20. So show it. So in general, let's develop the fixed moment formulas for the general loading. So if you have this general loading here, the idea is to consider a strip. Then that would be height of strip y times thickness dx, that's the differential p. Then assuming that the load is not coinciding the left end or the right end, nor the right end, then let us say its distance from the left end is x1 and the other end of the load is x sub 2 from the left end, and our limits would be from x1 to x sub 2. The distance of the centroid to be stripped from the left end is still a, which is equal to x, and its distance from the right end would be d or L minus x. So that's x sub 1 and that distance is x sub 2. So in general, fixed moment at the left, a is negative integral of dp, which is y dx, times a, which is x, d square, L minus x square divided by L square. So dp is y dx, x L minus x quantity square over L square. Our limits would be from x sub 1 to x sub 2. Likewise, for fixed moment b, we just interchange these two moment arms, so x is squared now, L minus x would be power 1. So let's have the derivation of the fixed moment due to a couple as load, because for a couple there's no load where you can cut a strip. So this is unique. And let's assume that the couple is clockwise in this case. So we have no other means of deriving it except to apply the basic approach, which is considering the moment diagram by parts. So let's make the far end as the wall. So in these formulas that we're going to derive, let's assume that all fixed moments are clockwise. So that's it. If the result is negative, then it means the fixed moment is counterclockwise. So this is the moment due to the reaction at n. The reaction at n is expected to be downward because the moment is clockwise. For instance, if the supports are simply supported, so reaction times L equals moment, right? So this is Rn L over EI, or since EI is treated as one, you cannot affect with fixed moment, so Rn L. Then moment at the near end, which we assume positive, like the one shown, fixed moment here. Then due to the load, we have another positive moment. And so for the first part, EI theta NF equals 0. So area above equals area below. So EI theta NF equals 0. So fixed moment here times L plus M times B, then equals this negative area. So 1/2 L times RNL. So next, RNL square over 2, simplifying, minus fixed moment near times L to the right equals MB. Call that equation A. Then we just add moment arms. Let's compute division of EI division of F relative to N, so that we sum up moment about F. So moment arms of these areas about F. So RNL square over 2 is multiplied by L over 3. Minus fixed moment near L times L over 2 equals MB times B over 2. So RNL cube over 6 minus fixed moment near L square over 2 equals MB square over 2. That's equation F. So that we can eliminate RNL cube over 6, we multiply equation E by L over 3. So it becomes RNL cube over 6 minus fixed moment L square over 3, then equals MBL over 3, equation F. Then we now subtract this new equation from this equation here, F. Then negative 1/2 minus negative 1/3 is negative fixed moment L square over 6 equals, what is common at the right side is M. So we have MB square over 2 minus MBL over 3. Then we multiply the right side by the reciprocal of negative L square over 6, or we multiply the right side by negative 6 over L square, and simplify. So we have fixed moment here is 6 over L square. Then we interchange because we treat this as negative, or we only distribute the negative sign. So MBL over 3 would now be the positive, and minus MB square over 2. What is common here is MB. Then factor out MB, then distribute 6. So you will have MB over L square times quantity 2L minus 3B. So that's the fixed moment here, MB over L square, quantity 2L minus 3B. Similarly, for the fixed moment part, it is MA. We just pattern the formula for moment fixed moment par from this result, ma over L squared times quantity 2L minus 3A. So for that equation 7, fixed moment par is ma over L squared, quantity 2L minus 3A. Equation 8. So remember that these are the formulas for computing fixed moment due to a couple. And in our assumption, we assume that the couple is, or this in this formula here, the couple is clockwise. And we assume that the fixed moments are clockwise. If the results in these calculations will be positive, it means that our assumption is correct, that the fixed moments are clockwise. But if the result is negative, then it means counterclockwise. I hope it is clear for that. Now, what if the load is counterclockwise? So you use the same formula, and we still use that the fixed moments are clockwise, and we replace m by negative m. So we apply the above formulas whether or not the point is in the left or in the right. So there's no confusion with that. You just apply the formula. Then if the resulting sign after using the above formulas will be negative, it means that the fixed moment is counterclockwise. I hope it's clear. Then for the case where load is counterclockwise, you just replace the m here to negative m, and the formula is the same. So fixed moment here is negative quantity negative m b over L squared 2L minus 3b. And fixed moment par is negative m a over L squared times quantity 2L minus 3a. So again, if the result is positive, so there's no problem. The fixed moments are clockwise direction. But if the result is negative, counterclockwise. This first example to illustrate the concepts on fixed moments. So let's consider this first example. Calculate the fixed moment or fixed moments for span AB and for span BC. EI is constant. So let's solve this into two ways. The first way is we imagine that the spans are fixed-ended and we apply area moment theorems. The second way, we use the direct formula by integration. So for AB, the moment diagram by parts, let's take A as the wall. You can make the wall anywhere, but the easier way is at A as the wall. So 24 times 5 times 2.5 is the moment is 300 and the curve is second degree. And moment due to 50 is 50 times 7, so 350 triangle. Then due to the fixed moment at B, I'll just call that MB, but it's really fixed moment at the far end, which is B rectangle. I assume the it positive just like before, so that whatever is the final value, that's the final answer also. And due to the reaction at B, then we have RB times 10, the span is 10, so 10 RB over EI supposedly, but EI is treated as 1. So for the EI theta AB, so we equate areas above to area below. By the way, for the second span, 1/2 of 3 times 45 times 1, it's 7.5 moment here. This is third degree. Now at the wall B, the moment is 1/2 of 3 times 45 times 1 plus 2, so 3 times 3, that gives us 202.5 over EI. Let's divide that into two triangles. Then for this couple, which is counterclockwise, so it is above from this point. So we have here fixed moment at C or MC. We assume also that it is positive counterclockwise. Then the moment due to reaction at C. This is 9, so 9 RC. By the way, this is the moment due to the couple. It begins at this point only. Then moment due to reaction at C, which is triangle 9R sub C. That's it. So for span AB, the area, fixed end moment BA, so that's BA or fixed end moment B or moment B, times 10, so 1/2 of 10 times 10 RB plus 10 times MB equals, we have two areas here, 1/3 of 5 times 300 plus 1/2 of 7 times 350. Simplifying, we have 50 RB plus 10 MB equals 1,725. Call that equation 1. Then for EI division of A relative to the tangent of B, remember B is fixed, so we just incorporate the moment arms. So 50 RB times 10/3 plus 10 MB times 5 and equals 1/2 of 5, 300 times 5/4, which stands for second degree, 5/4, plus 1/2 of 7 times 350. Moment arm from A is 1/3 of 7, or 7/3. Simplifying, we have 500/3 RB plus 50 MB equals 10,450/3, equation 2. Solving these two equations simultaneously with our calculator, and R sub B is 61.7 kilonewtons, MB, which is the fixed moment BA, is negative 136 kilonewton meter. So that's it. Then we can now compute fixed moment A, which is just the sum of these moments here. So 10 RB plus MB minus 300 minus 350. So moment A, which is fixed moment AB, is 10 times RB plus MB, which is negative 136, minus 300 minus 350. So fixed moment AB is negative 169 kilonewton meter. Then, so that shows that fixed moments are really negative. Then we have for span BC. For the shortcut, fixed moment AB is integral of 24 dx, that's dt. Then, because this is AB, then it should be x, the distance is x, then B is 10 minus x, quantity square, divided by 10 square. Then for the concentrated load, so minus 50, our A is 7, then B is 3, so 7, 3 square over 10 square. So computing that integral combined with this value, the result is negative 169 kilonewton meter, just like this. Then for BA, for the integral, you just replace the x now is squared, then 10 minus x will be raised to 1. Then likewise for the concentrated load, 7 now is squared, then 3 is just 3 divided by 10 squared. Limits, by the way, 0 to 5 because the rectangular loading has a length of 5. So computing this value, it is equal to negative 136 kilonewton meter. This is the same as this. So that's the advantage of integration. There's no need to draw these diagrams there, and the solution will be faster. Then for BC, EI theta BC is, or area above equals area below. So we have 1/2 of 9 times 9 RC plus M sub C times 9, then plus 120 times 7, or 7 times 120, equals, so for the area, we have third degree curve and trapezoid. So the third degree is tilted third degree, the trapezoid is trapezoid because we are just computing area. So for the third degree curve, 1/4 of 3 times 67.5. Then for the trapezoid, 1/2 of quantity 67.5 plus 202.5 times 2. So simplifying, 40.5 R sub C plus 9 MC equals negative 519.375. Call that equation 3. Then for division of B, because the wall is B relative to the tangent at C, we just incorporate the moment arm. So 40.5 times 3. Distance of centroid of this triangle from B is 3. Plus 9 MC times 4.5. Then plus 7 times 120, because this is only 7, so the moment arm is 3.5. Then equals, for the third degree, 1/4 of 3 times 67.5. The distance of the centroid from this end is 3 over 5 or 0.6. Then plus 2, so 2.6. Plus, for this small triangle, 1/2 of 2 times 67.5 times 2/3 of 2, which is 4/3, plus this remaining triangle, 1/2 of 2 times 202.5 times 1/3 of 2, so 2/3. So simplifying, we have 121.5 R sub C plus 40.5 M sub C equals negative 20,667 over 8. Solving equations 3 and 4 simultaneously, R sub C is 1313 over 324, and fixed end moment CB in decimal is negative 75.944 kilonewton meter. Then for the fixed end moment BC, which is here, it is equal to 9 R sub C plus 120 plus M sub C, then minus 202.5. So fixed end moment BC is 9 times R sub C, this is the R sub C, plus 120 plus MC, the fractional or exact value of MC is negative 1367 over 18. So that's actually that value there. Then minus 202.5. So fixed end moment BC is equal to negative 121.972 kilonewton meter. Then by integration, we consider strip here. The height is 45. Let's call this x. Then the height of this strip is 45 divided by 3. So that's 15. So the height of the strip is 15x. Then the distance of the imaginary concentrated load, differential concentrated load from B is, because this is 5, then the distance is 5 minus x, while B is, its distance from the right is x plus 4. So fixed moment BC is integral 0 to 3, so negative of quantity 15x dx dt. Its distance from the left, or A, is 5 minus x. Its distance from the right is x plus 4 quantity square over 9 square. Plus, because this is counterclockwise, using the formula negative 120, B is 2, the distance of the copole load from the right, that's B, which is 2 over L square, 9 square, quantity 2L minus 3 times 2. So, computing, fixed moment BC is negative 121.972 kilonewton meter. While for fixed end moment CB, remember that due to the load, it is expected clockwise. That's why we put negative sign. So clockwise, it is expected clockwise. Remember, fixed end moment, it's counterclockwise here. For fixed end, remember the curvature, counterclockwise here, then clockwise here, so that the beam will bend concave downward, so negative. But let's compute the fixed end moment here by integration. We consider it, the sign, as positive, so it means it is expected clockwise, then plus the moment result in the second part. And let's compute also the moment in the second part. So fixed moment equals 0 to 3. So because it is anticipated clockwise, 15x dx, then interchange the squared. So 5 minus x squared now, x plus 4 over 9 squared. Then plus negative 120. A is 7. The distance of the copulode from B is 7. Divided by 9 squared, quantity 2 times 9 minus 3 times 7. The result of the second term is, this is 2 times 9 minus 3 times 7. This is negative times negative, so positive. Because the second term is positive, it means it is clockwise. So that's why we have to anticipate that because this is also expected clockwise due to the loading, then they will add. So adding the two, the result would be equal to positive 75.944. Why is it positive? Because they are clockwise. But clockwise is clockwise moment at the right end, that's negative moment. So friction moment CD, the result of this calculation is 75.944. So we indicate clockwise so that it is the same as this result. It is negative 75.944 because at the right end, the friction moment is expected to be clockwise, and friction moments are, remember, negative. That's it. So they are equal. We have already calculated friction moments, and they are negative in reality. Or in other words, at the left, it is counterclockwise, and at the right, it is clockwise. Let's now have the sign conventions in applying the slope deflection equations, because remember, in slope deflection equations, clockwise moments, clockwise rotations are positive. So how do we compute, or how do we give sign or signs to fixed moments that you have calculated? So if the moment matches with the sign convention for slope deflection equations, then that is clockwise positive, then we will do that here. So positive moments are such that the beam will bend in a smiley curve. That is, this is the really the positive bending, and this bending will only occur if the moment at the left is clockwise and the moment at the right is counterclockwise. I hope you can imagine that this is positive moment if the moment at the left is clockwise. Just imagine you bend a material, you get a material which is elastic and try to apply clockwise moment at the left, then counterclockwise moment at the left, so that you can see that that's positive moment. So clockwise at the left, counterclockwise at the right. So that the negative moment would be opposite to that. It's a sad curve, sad face curve. So which is counterclockwise at the left, then clockwise at the right, which is the fixed end moments curvature, if you can remember, due to the load. So clockwise, counterclockwise, that's positive. So this is the universally accepted sign conventions for all cases. So universally accepted and correct description of positive moments. Now, what's the effect of the load? In general, loading not due to a couple, because a couple might change. We assume clockwise at both ends. And if the result is negative, that's the time we conclude that it is counterclockwise. Now, for loading, it is natural that the bending of the beam due to this loading is such that we have sad and sad bending or negative bending at the walls. We only expect positive moment somewhere in between those walls. Here, this is similar in shape as this. But at the walls, we expect negative fixed end moments or bending. So that at the left end, because this is negative, the direction is counterclockwise. So we have negative moment there, negative moment there. So this should be counterclockwise. This is opposite to that. So that at the left, and on the other side, it is clockwise. Therefore, because it is only the other side of moment which is clockwise, and it matches with the sign convention for slope deflection equation. Therefore, when we compute fixed end moments, I now change the letters to L and R, meaning left and right end. Therefore, if you set up equation for moment at the left end, then the fixed end moment is negative, because we expect that at the left end, the fixed end moment is counterclockwise because it's negative. Therefore, when we set up moment L, it is 2EI over L times quantity 2 theta L plus theta R minus 3 times delta over L. Remember the trigonometric, the slope deflection equations. Then plus fixed end moment left. This fixed end moment left is negative. The sign should be given negative because it is expected counterclockwise. And for moment RL, or moment at right, so it is equal to 2EI over L quantity 2 theta R plus theta left minus 3 times delta over L, then plus fixed end moment right, which is positive. So this is the explanation, and I hope it's clear here in the drawing. Since for slope deflection equations, clockwise moments are positive, and the effect of the load is to produce counterclockwise moment at the left and clockwise moment at the right, for the moment to be negative, then at the right, the fixed moments are using slope deflection equations would be fixed moment L is negative. The sign is negative because it's counterclockwise here. Clockwise is positive in the slope deflection convention. And in the right side, it is positive. So plus fixed moment, so if the point is at the left, that fixed moment is negative, or in other words, it's counterclockwise. Then for moment RL, then when you add fixed moment right, then it is positive because it is expected clockwise. So example 2, calculate the moments at A and B for the beam shown EI is constant. Let's now apply the slope deflection equation so that you can study why the fixed moment for one equation is positive and the fixed moment for the other equation is negative. So this is the loading. For easy calculation of fixed moments. So let's set up moment AB. So moment AB is 2EI, which is treated 1 here over L. We use the formula 2EI over L, 2 theta near plus theta far minus 3 delta over L, and plus fixed moment near, because we expect moments at A and B. So we apply twice. But for B to C, the moment at C is 0, so we apply the other formula, which was 3EI over L, quantity theta near minus delta over L plus fixed moment near minus 1/2 fixed moment far. So for moment AB, this is the formula, 2 times EI, which is treated 1 here, over, because EI is constant, over L, which is 9, quantity 2 times theta A. Theta A is 0 because that's fixed. Plus theta B, we expect rotation at B, minus 3 times delta over L, which is 0 because the supports are unyielding, no settlements or relative settlements. Then plus fixed end moment here, because if we consider AB, A is in the left side, and we expect the fixed end moment at the left side to be counterclockwise. That's why it is negative. The sign is negative. So W 9 square over 12. You see the point? This is counterclockwise due to the load. The bending here is counterclockwise and the right side clockwise. So that's why it's negative, because A is in the left. Simplifying, we have MAB equals 2 over 9 theta B minus the load, which is 135. Fixed moment is negative 135. Call that equation 1. Then for BA, we also have BA, the same equation. So 2 times 1 over 9 times 0 plus 2 times theta B minus 3 times 0, then plus 29 square over 12. Why is it plus? Because at the right end, fixed moment is clockwise for it to produce negative curvature. So it is clockwise, and clockwise moment is positive in the slope deflection equation. So that's why it's plus. So 4 over 9, and BA is 4 over 9, theta B plus 135. Call that equation 2. Then for BC, again, we use the other formula here, 3EI over L times quantity theta near. Our near end is B. Then minus delta over L, which is just 0. Then plus fixed moment near, so fixed moment at B, which is left, so negative, minus 1/2 fixed moment right, which is fixed moment sa C, because C is right, it's positive. So moment BC is 3 EI1 over L6 quantity theta B, theta near, minus delta over L, which is 0. Then minus our plus fixed moment B. Fixed moment B is negative because it is left here, counterclockwise expected moment. So minus 45 times 2 times 4 square. 45, A is 2, B is 4, 4 square over 6 square. Then minus 1/2. So this is fixed, minus 1/2. Then the fixed moment at the right end, because it is the right, C is in the right side, we expect clockwise moment there, fixed moment there. So that's why it's positive. Positive of 45 times A, you interchange the squared items here. So 2 square and times 4 divided by 6 square. So simplifying, MBC is 0.5 theta B and minus 50. Call that equation 3. Since B must be in equilibrium, so the moment BA plus the moment BC is 0. So MBA plus MBC equals 0. So MBA is 4 over 9 theta B plus 135 plus MBC 0.5 theta B minus 50 equals 0. Finally, we can solve theta B. Theta B is 50 minus 135 divided by the quantity 4 over 9 plus 0.5. So theta B is negative 90 over EI. Remember that we do not include EI here. We assume it is 1, but when you compute for rotation, it is equal to value divided by EI. We can now compute moment at A. We substitute the value of theta B in equation 1, but of course we remove EI again because supposedly there is EI here, to theta B over 9 EI, but we just ignore EI. Moment AB is the moment at A, and the moment at B is also moment BC, not moment BA, because moment BC and moment BA are numerically equal, but they have opposite signs. So of course, we expect moment BA to be positive because it is in the right side and it is clockwise. Moment BC is B is in the left, so BC is in the left. B will be in the left, so it is expected counterclockwise. That's why it's negative. So moment AB is equal to moment A is 2 over 9 times theta B negative 90 minus 135. So moment A is negative 155 kilonewton meter. Moment B is equal to 0.5, moment BC, 0.5 of negative 90 minus 50. So that's why it is negative 95 kilonewton meter. So I hope that you know the reason why these moments are negative, because the curvature of the elastic curve will be concave down here, and at B, of course, the deflected shape will look like this, then concave down here. So that's why moment B is expected negative, concave up, and 0. So that's why the moments are expected negative.